This is the first experiment on the second amplifier stage. I'm using negative feedback through this capacitor. It is the gate-to-drain capacitor of the FET itself. With 20 FETs, it's about 36 pF according to the data book. Then there is an inductor in the sources, 0.1 microhenry. This inductor shifts the current through the transistor by 90 degrees with respect to the gate voltage. This capacitor gives another 90-degree phase shift. As a result, the feedback is 180 degrees. So there is a low impedance on the gate, and I have tuned it to become close to 50 ohms. In order to do that, I had to add 2 microhenries in series. These 22 microhenries is for DC grounding only and not intended to affect the impedance. And a capacitor to isolate for DC. On the drain side, I haven't made a proper solution yet. I just put something here, some winding, and this capacitor to get a reasonable impedance and frequency response. To measure the noise, because that is what I want to do first, I have to present 50 ohms to the correlation system, the 2-channel receiver, and in order to do that I had to add this network, which is pretty lossy, but it gives me a 50 ohm impedance here. 0.1 microhenry is about 6 ohms on 10 megahertz. I want this to be noise-free, means I want to avoid ohmic losses. So it is a fairly thick wire. There are 2 capacitors in parallel to minimize the ohmic component of the reactance it might have. Then this 1 microhenry inductor is intended to isolate the source from the thermal noise from this resistor. It is decoupled, but connecting it directly here could give some degrading of the noise figure. I have seen that phenomenon on VHF amplifiers, and there is no disadvantage adding these extra components. Here is input impedance and gain over a bandwidth of 19 MHz, centered on 10 MHz. And it's 7.5 dB gain, and the impedance is 42 ohms and nearly resistive. So this is close enough to start with. And here is the output impedance, 54 ohms and 4 ohms imaginary part. And the isolation is 26 dB on 10 megahertz and a little bit less at 13 megahertz or so, but this is significantly better than the forward gain. I'm going to feed this amplifier from something very far from 50 ohms. First I'm going to try tap number 6 of my first stage, where the impedance is 2 kilo ohms with an imaginary part of 500 ohms. And that is on the center frequency. On the sides there will be 7 kilo ohms. As an alternative, tap number 4 has 2 kilo ohms on the sides and 770 ohms on the center. First I'm doing this experiment, feeding the amplifier through a 2 kilo ohm resistor. Here is the phase noise. it shows about minus 137. And here is the amplitude noise, and it looks very similar. And here are both of them. And we can see there is some sideband noise at close range, below 100 Hz. About 1 dB for the phase noise extra at 50 Hz. Maybe this is caused by noise on the supply voltage, I don't know. And then here the noise is a little bit lower. I think that is an artifact of my test system. 8 dBm at 50 ohms means 6.32 milliwatts developed in the 50 ohm load. The electromotoric force is then 1.124 volts. So this is the equivalent circuit diagram. EMF 1.12, 50 ohms, that's the source, the resistor, and the amplifier. With this driving force, the current becomes 5.37 milliamps, and with that current, the voltage drop on the input of the amplifier, 42 ohms, will be 0.226 volts. Then, at room temperature, the noise power of any resistor is minus 174 dBm for 1 Hz bandwidth. That is 4 times 10 to minus 18 milliwatts in 1 Hz, or 0.4 times 10 to minus 20 watts in 1 Hz. In a 50 ohm resistor, these two resistors, they generate the thermal noise. The voltage can be computed from the power, and I get 2.8 times 10 to minus 9 volts in 1 Hz bandwidth. Into the amplifier, I get 42 divided by 20, 92, 42 divided by the whole, and that is 0.56 times 10 to minus 8 volts in 1 Hz. Then I can compute the signal-to-noise ratio if I assume the amplifier doesn't add anything. Means 0.226 divided by 0.56, and that gives me a voltage ratio here, and the square of that is the power ratio, and converted to decibels, it comes as minus 168 dBc per Hertz. And this is all of the noise. Half of that is going to be phase noise, means the phase noise that I could observe if the amplifier is noise-free should be minus 171 dBc per Hertz. What I did see was minus 137. To that comes 29.7, that was the carrier suppression of the interferometer. Means I observe minus 167. And I conclude from this that the amplifier adds 4 dB to the phase noise when the source is a room temperature 2 kilo ohm resistor. When using the second amplifier as intended, following the first amplifier, the power level will be the 8 dBm that comes in here, minus 7.4 or minus 11.4, depending on which tap I'm going to use. Means normal operation is with about 0 dBm into the second amplifier. And that is from a high impedance source, I cannot generate that easily, but I can see what I will find with 0 dBm directly into the 50 ohm, or rather 42 ohms of the unit. The carrier is a 0 dBm signal from a 50 ohm resistive source. It means that the white noise from the resistive component of the signal source has to be minus 174 dBm per hertz. So the phase noise should be minus 177. Now with the 30 dB offset I have, that comes as minus 147. That is here. And we can see the noise seems to go asymptotically towards this. It's only 1 dB higher here, and this is 1.1 kilohertz. But the phase noise at close range that I see here, it looks very similar to what I had with the 2 kilo ohm resistor in series. At 50 hertz, here I have the 50 hertz spur, I can see minus 136.8 or 7 or so. In this measurement, with 8 dBm through 2 kilo ohms into the amplifier, the power at the output is minus 10 dBm when I measure with the 50 ohm spectrum analyzer. This means that with the 2 kilo ohm resistor in front of the amplifier, the noise at the output, the thermal component, is minus 181 dBm per hertz. That's a bit below room temperature, while the total noise is minus 177. That is the same as room temperature, so there is no excess noise when the impedance is as high as it will be when this is running with the first amplifier connected to it. So it will amplify whatever noise the first amplifier produces, but it will not add its own noise when followed with an amplifier with 0 noise figure. And this is for wide separations. At close range there is this extra noise, but I don't know the origin of it, but it could be flicker noise from transistors, or it could be modulation from the power source. I'm feeding the amplifier from this battery now. It gives a little higher, 20.5 volts. I was running 16 volts before, but I can see fairly quickly that the phase noise at close range at 50 hertz, it looks like minus 136. I haven't waited long enough. Maybe I wait some more. But this is not noise from the battery, I cannot imagine. So it has to be the transistor that is causing this. The voltage is dropping slowly, but the interferometer is not affected. It means the gain isn't changed by this small voltage change. A little more time has passed, and I can see at 50 hertz minus 135 on this scale. And I have a look at the amplitude noise also. And it is actually better now than the phase noise. With the power supply it was the other way around, as I can recall. I have to repeat that. Now I'm back on the DC power supply, running at 16 volts, and the phase noise is at about minus 137. And now I check the AM noise. And indeed it is significantly better than the phase noise at about minus 139. So my memory failed. There is no difference between this power supply and the battery, except that the battery gives a little too high voltage, so the noise isn't quite as good. Suddenly the amplifier started to misbehave. You can see that in the waterfall. There is more noise, and less noise. And this is the proper operation. Something is unstable. And it's visible also in the narrow band waterfall. You can see this band of better performance. And the phase noise is now minus 136.5, and that is the average over nearly 5 hours, while this noise has been coming and going. And the amplitude noise is fairly high at here 128.5. And remember, there is 29.7 dB of suppression due to the due to the interferometer. It took me quite some time to find that the problem was caused by the coil. So I have made a new coil here, and you can see how the taps are made. I've bent the wire outwards and soldered rather carefully to avoid problems with poor contact due to the enamel of the wire. Here is the wire from the previous winding with one of the taps, and as you can see it is not properly soldered, and I think this was the reason for unstable generation of noise from this coil. There were many taps. This is the worst one. And here is one of the good ones. It is properly soldered from all sides. I have selected the point nearest to the drains, and I am looking with the oscilloscope, and I have connected it also to the output where I have a 50 ohm load. And the signal level I see is 430 millivolts peak to peak. And here is what I see on the network analyzer. The bandwidth comes at 1.26 million, and the gain is minus 8.2 dB. It's similar to what I saw before, of course. Here is the performance I see now. I just started collecting correlation averages. And it fairly rapidly goes to about here, that's minus 136. But I have to wait for a while. There is still a problem. The track at the center is wider as compared to when I started. And you can see the noise bursts coming. Here it's lower, and here it's higher. And the width of the white section in the center, difficult to see in the camera, but it varies. And it was significantly narrower when I started this collection of data. And when I look here, I see 136.5, and that is not compatible with the value I saw just when starting this measurement. I tried put heat at various places by use of this heat gun. That wasn't a very clever idea. I forgot about polystyrene capacitors. They have a very limited temperature range, So it ended up in a short circuit and black smoke because of the big capacitors I have in the power supply. Now the first amplifier stage looks okay. It shows 138.5 or close to that after 25 minutes. And the noise in the waterfall here, it looks quite stable and at a little bit lower level than before. I don't know why it's better, if it is the heat treatment or if it was a problem with that polystyrene capacitor that I have replaced. Now, almost 10 hours later, things look okay still. The noise floor at 50 Hz offset minus 138.5. And the waterfall doesn't have any signs of unstable noise sidebands. Hopefully this is permanently okay, but since I don't know exactly what the problem was, it is possible it will come back. To get an idea about the precision, I changed the mode and show phase noise only. At 500 Hz, I see minus 149. At 500 Hz, I see minus 149. Here is what the second stage looks like now. There are no inductors in front of the FETs anymore. Instead, I have tuned the output a little off frequency. There are many capacitors on the drains, and this coil is rather small, and there is some resistance in series, and since the signal level is going to be fairly high, I don't care about the impedance on the output. That should be 50 ohms to make the correlation receiver show the proper noise floor, but with the higher signal level it will do accurate enough anyway. Here is what I can see on the network analyzer. The impedance is accurately 50 ohms. The gain is 8.7 dB on 10 megahertz, and it's a little bit higher, maybe 11 or so, a little bit lower. But that is of no interest. I'm not interested in what happens more than 100 kilohertz from the center, because there will be more amplifier stages that could add some selectivity with LC circuits. I have connected the second amplifier to the output of the first amplifier. The sweep width is now 1 megahertz. The impedance is in the order of 100 ohms, and it doesn't change with frequency much. Here is what I see through both amplifiers. The filter, the first amplifier, and the second amplifier. Gain is 0.7 dB and Q 1.27 million. Something could have changed, so I look again at the input of the second amplifier stage. And what I see is 506 millivolts. Not much of a difference, but a little. Now I am sending nearly the same signal level from a 50 ohm source directly into the second amplifier. Here is the phase noise, started to collect right now. And it looks good. 50 Hertz, here minus 139, but the imaginary part is equal as the real part. So I have to wait for a while. The noise floor seems to be flat all the way down to 50 Hertz. Here, minus 142. The 50 Hertz spur comes in the imaginary part this time. It varies from time to time. I can compare this with what I saw from the first amplifier, here. And at close range, the second stage is much better. At wide range, I don't know, because I haven't waited long enough. And I will not do that either, because there are other things to look at. I'm sending the same signal level into the second amplifier, this time through 230 ohms. That's 217 in parallel with 1500 ohms. And indeed, the signal level is very similar. This is more favorable since I don't need an attenuator on the output of the box anymore, because attenuation is through that resistor. So the interferometer works with a higher signal level, means the noise floor here is lower. So already after this is half a minute, I see the noise floor at minus 146, and it looks flat. And so this second stage shouldn't contribute anything to the noise from the first state. Here is the noise of both amplifiers in series, and the signal level is the same as when I went in with the resistors, so convergence is a little bit faster. At 50 Hertz it looks like maybe minus 138 or so. So that's the first amplifier stage. And what will happen at higher offsets, I don't know yet. Already after about 10 minutes I have a reasonably accurate sideband noise measurement with respect to the statistics. I can compare this to what I have been seeing on the first amplifier only, which is this. And it's clear phase noise at close range has degraded by about 1 dB at 50 Hertz. It's a negative peak here. Well, and at 20 Hertz here, no difference. But at wide range, let's say 300 Hertz, there is a significant difference. So there is a wideband noise from the second amplifier. Whether that really is wideband noise added, or whether it is a measurement error here, where the signal level is very low and where the impedance is not 50 ohms into the correlation, two-channel correlation system. I don't know. Anyway, this looks promising. Minus 144 here. That corresponds to minus 174 dBc per hertz, because I still have 30 dB suppression from the interferometer. The signal level on the drains of the second stage is 3.7 volts peak to peak. These resistors combine to give 92 ohms, and I had 3.7 volts peak to peak, loaded by 92 ohms from the resistors and 50 ohms from the measurement system, means 142 ohms. So the power developed in the load means the resistors plus the 50 ohm measurement system is 12 milliwatts. So that is plus 10 dBm, or more like plus 11. So putting a resistor there and using the voltage across that resistor to feed some amplitude limiting device, that will be the next stage towards converting this into an oscillator. There are still occasional noise events like this one, and as you can see also here, the sharp line is that Linrad has moved the frequency a little bit to keep the carrier at the center. This is normal and does not affect the results. Nevertheless, the phase noise now is at minus 138, means minus 168 dBc per hertz for the phase noise. And I have an amplitude limiter, a very simple one, so the AM noise is not as high as I have seen before. The result from the first amplifier that I have saved is here, and you can see that above about 30 hertz or so there is a degradation now, and it's significant here. This is the saved result, and this is what I have now. So it's a couple of dB. But now the impedance is correct, it's 50 ohms. So what I see out here was probably, or could have been, an artifact because of the impedance error. Anyway, at very close range here, the old result is here, and the new here is better. If you look at, let's say, minus 130 dB, it's clear that the curve jumps outward when I go to the save data. But it's the other way around at 50 hertz. 138.5, and here it is 138. But this includes these noise events, and I don't know how to find the origin of those, so I will live with them with this particular unit. I added these resistors in order to prevent oscillations in the VHF range. I changed the drain side like this. Now all the energy on 10 megahertz is dissipated here. This will be shunted by the small inductance. So I think this is more favorable. Anyway, it gives exactly 50 ohms at this point, exactly like the previous arrangement. I have added a third amplifier stage with a limiter. There are 8 J310, several turns on the drain, a single turn for feedback to the source, and then a second turn to get the output. There is still a very low impedance here, so 47 ohms in series gives me a 47 ohm signal to use for the output. Then the drain, there is a high voltage there, a capacitor and a fairly high resistor into two diodes, one N4148. And then I get a square wave. This delay line, 7 LC links, 56 microhenry, 220 PF, gives the appropriate delay to set the phase right at the output, where I have 8 dBm sine wave to use for feedback. And here is what it looks like. Transistors and the delay line and the transformer here. And I have been running it for a while, not a long time, well, 3 hours already, and it looks promising. At 50 Hertz, it looks like minus 167, but it's still fairly flat. And at 20 Hertz, the imaginary part and the real part have the same size. So it's too early to say something about what performance might be. And further, the box is open and there could be interference from the outside. So I will put the lid on and restart, and also with a little higher resolution for the correlation spectra. My 2-channel receiver is not really good enough for this. Particularly the channel 2 local oscillator, the red trace here, it's not as good as the one I have for channel 1 by 4 dB or so at 30 Hertz. The observed phase noise, the yellow track here, is at a constant level below the uncorrelated spectra, like this, all the way. I have to take the average of these two curves. It means I don't really see the phase noise of my oscillator yet. The imaginary part and the real part are very similar in magnitude. This is after 11 hours and 47 minutes. At least 24 more hours have to be collected before I can say something with a reasonable certainty, I think. But there is always the danger that my system fails. The two local oscillators, these are phase locked, and when temperature changes, they drift differently and may go out from the locking range, which would require a restart and hope for better luck next time. So I will leave this running to see what happens. This is 34 hours in a compressed x-axis. Here I can see that 50 Hertz is 169. 25 Hertz, it's here. 165, but a bit uncertain. And 100 Hertz, 172 or maybe 173. Statistics is not good enough yet, but this is something that I have, and I would need another many hours to get more reliable results, and maybe the system won't work as long. Here is phase noise and AM noise at the same time. The phase noise is lower than the amplitude noise in this region, but it's not very obvious. When I use the compressed scale, like this, it is much more visible here. This is because averaging is done on the complex spectrum, and that evens out the variations from bin to bin. And then the power is calculated on the averaged complex spectrum. This is after 54.5 hours. The system has failed. The two oscillators of the two-channel receiver have lost the phase locking. So from this point, data is useless. But I have saved data from some earlier time, and I will try to evaluate that. This is 46 hours, and if I read 100 hertz, something like this, 172.5, 50 hertz, about here, 169, and I cannot read below 25 hertz because the imaginary part is equally strong as the real part. But I can look at the compressed spectrum, which I also have saved, and I can look again at 100 hertz and 172.5. This seems to be a reliable result. 150 hertz, that's this peak, and I would say it comes here, 174. 50 hertz, this strong peak, 169.5. And maybe halfway, that's 25 hertz here. Minus 165. And my system isn't good for doing this better than like this, unfortunately. The output from the oscillator looks like this. 14.6 dBm is the signal level, and overtones are not very strong. I have connected the Wenzel oscillator. Starting here, it drifts into the right frequency, and then I connected it properly, and it's still drifting a little, but not so much. And I will have to wait for a while to see what the performance might be. I think with my oscillator I couldn't see the noise here, but I'm not quite sure. We will see on the phase noise within probably a couple of hours. Here is nearly 8 hours with the Wenzel oscillator. The mouse is at 25 hertz here, and I see 154.5 dBc per hertz, minus 154.5. And 50 hertz, it's this spur, that is 159.5. 100 hertz, it is this spur, minus 163. And 150 Hertz is about here. Well, maybe a little lower here. And that is 164.5. I can compress the x-axis, and maybe that will make it easier to read. 0.1, like that. Then I see 50 Hertz, 159.5, 100 here, 163, 150 is here, 164.5. This is much easier. I look at the amplitude noise also, and it's very low. And here is amplitude noise as well as phase noise. So I think there is a limiting amplifier at the output of this unit. The amplitude noise is similar to what I see from my own design. And I can try to get some kind of value at 10 Hertz. That's here. And it is rather uncertain, but in the order of minus 146 or minus 147. I exit from here and go for the parameter menu to show the parameters I have been using here. Like this. This is for close range measurements. And I can leave this the same. It doesn't really matter. This is slow for the main waterfall. But I want to look now at a wider frequency range. So I make the first mixer bandwidth reduction smaller. It has been 5. I make it instead 3. That is a factor of 4 smaller. And then, of course, I cannot have as narrow baseband bandwidth anymore. It becomes wider because I cannot have more than 16-bit for the addressing in the Fourier transform. And I will look here with some different size for the FFT to have a fairly quick collection of the data. I can no longer do processing in the time domain, so I had to click here to change from 2 to 1 to do the processing in the frequency domain instead. I mean the baseband filtering, and I set a suitable baseband filter like that and click on the signal and move it to the center. Oh, it was doing that automatically, so I have to move it back again. And then I want a smaller transform size, change from 15 to, let's say, 12. That's a factor of 8. And I made a factor of 4. So that is 32 times faster now. And I can see up to 400 Hertz. Now the first FFT bandwidth is 2 Hertz. and I can see up to 2 kilohertz offset. And I will have to wait some time, but not a very long time. Already after half an hour, I have a reasonably accurate result up to 2 kilohertz. Like here, that's minus 169, plus minus half a dB or so. I can see at 200 hertz, it must be this little peak, 165.5, just as I have seen before. But I can compress the x-axis, 0.1 here, which is equivalent of using a much larger transform. But the line width become narrower on the screen. So I can see that 2 kilohertz, that's here, minus 170, and it looks flat here. So this was the Wenzel oscillator. I have connected my own oscillators, and it has started from cold, and it's gradually getting into the operating temperature 65 degrees on the crystal. The frequency drift is still too rapid for this algorithm to work, so this result here is probably not really valid. But soon it will be stable enough. This is 5 hours now, and the mouse is placed here, and that is 175.5 minus 175.5 dBc per hertz, and it looks flat all the way here. This is of course the DC, I mean 700 hertz, that's the offset from my direct conversion receiver. If I compress the scale, I may be able to see a little bit better. 0.1. And then I can read here at 2 kilohertz, 175.5. And I can take the average of this whole thing. I have plotted my findings from this video on this graph, where I also have some published on the internet information from good oscillators. They are specified here. The Wenzel, the one that I have, 501 25 420. Here is an old measurement I have made on that. Today I have found these green dots. They differ, but not much. And that was an old measurement. I don't remember exactly what I have done since. Anyway, from these green points I can decide that the B minus 1 is this green line. It looks like a straight line, this little section here. And then it starts to go up like that. It should have a B minus 3, means F to power minus 3. The red dots are for my oscillator, and they show a very clear straight line like this. It's the B minus 1. It comes at minus 152, while the Wenzel comes at minus 142. So this is 10 decibels better. The B0, the flat noise floor, is this red dot for my oscillator, and the Wenzel is about 6 decibels up, or 5, I don't remember exactly. Then theory tells me that the Leeson frequency theory is from here. The Leeson frequency is the frequency 10 megahertz over 2 times loaded Q. This is a paper by Enrico Rubiola and co-author Vincent Giordano. And doing the computation like that, it tells me that I should expect the straight line to continue up to this point, and here it should start to slope 30 decibels for a 10 times change of the frequency. But that is theory, and the theory assumes that the crystal is perfect and that the only mechanism is the flicker noise from the amplifier that goes through the crystal. But if the crystal itself produces flicker noise also, that will add, and this line would move somewhere, but not further than this, because I have this data point here. So this is as far as I can come with the equipment I have today.